All right, so today we're going to review what we learned the past few weeks for convection. So convection review. First off, exam is in 2 days. So that will be obviously online now, not going to be in class. But expect to do it at the same time. So normal time that class would have been when this exam was actually scheduled for. Obviously all the convection material, so that's only subject for this exam is convection, chapters 6 through 9, including those endpoints. It is open book, so that's no longer a question mark. That is definitely open book. You will need lots of tables, as you may have noticed throughout the homework assignments, all the fluid properties, A4, A5, A6. And then there's some nice tables that summarize the convection equations. So 7.7 for the external flows, 8.4 for the internal flows for forced convection, and then 9.3 gives you the free convection equations. So those are nice things to have handy or to bookmark while you're doing the exam. Exam time will be the same, so 75 minutes again, but format's going to be completely different because normally I'd have 3 questions on there. Instead, easier thing to do online is to break those up into kind of smaller parts. You've kind of seen basic procedure, as we'll see again today. Involves basically 6 steps. So 5-ish steps for 3 questions. I figured a good amount of questions would be 15 questions instead, so 15 small questions as opposed to 3 big questions. So topics, chapters 6 and 7, the external forced convection, laminar boundary layer over flat plate, turbulent boundary layer over flat plate, and then heat transfer across other external objects, cylinders, spheres, things of that nature. Chapter 8 was internal flows, so internal heat transfer generally in a pipe. And then chapter 9 was free convection, started off with the vertical plate and did other geometries after that. Then here's this basic procedure that I mentioned. So the 6 steps. First thing, find the film temperature, possibly bulk temperature if we're dealing with the tubes. Again, just the average wall temperature plus T infinity divided by 2. Second step is find all the fluid properties at that film temperature. So probably from table A4 for air and other gases, A6 for water, gives you the values of everything you need: density, viscosities, thermal conductivities, heat capacities, whatever you need. Third step is calculate the Reynolds number, because a lot of properties depend on the Reynolds number. That's for the forced convection case anyway. So that's why it's little question marks here. Reynolds number question mark, because if I'm dealing with free convection, I might need the Rayleigh number, so the Grashof number, Prandtl number. So whichever one you need to calculate based on whichever equations you're using, whichever geometry you need to deal with, basically for part 4, based on what you just did in part 3, and other conditions such as the geometry, what is the appropriate equation to use for the Nusselt number. So we'll go through all those because that's the one step that actually kind of changes what equation am I using. You're still finding the Nusselt number, but which equation you use, there's a lot of different equations as you've seen. Once we have the Nusselt number, H value is simply K Nusselt number over L, or could also be diameter, again, depending on the problem. If I have a cylinder or a sphere, I'm looking at diameter here. Reynolds number, again, could be D or L, depending on the geometry. And finally, find Q. So Q is just HA, T wall minus T infinity, A being whatever the surface area is. So it started off with the laminar flat plate in forced convection. That was the easiest case. The transition from laminar to turbulent happens at roughly 500,000. So anything below 500,000 is laminar. Anything above 500,000 is turbulent. The laminar velocity profile looks something like this. So 3/2 y over delta, delta being my boundary layer thickness, y being the distance from the plate, minus 1/2 y over delta cubed. That's my velocity profile, so how close it is to U infinity. Basically equals U infinity at y equals delta. Boundary layer thickness, delta over x, so again, x being the distance from the leading edge of the plate, 5.0 divided by the Reynolds number at that location. So again, Reynolds number has a length in it, it's location x, wherever that distance is. Gives me the boundary layer thickness at that point. And then the Nusselt number for this case, assuming I'm heating the entire plate, so there's also an equation that's different if I have an unheated starting length. that you saw during the homework. Also have this factor of 2 accounted for. So the official equation is 0.332, but they have to multiply by 2 later. I just do it now. So my Nusselt number 0.664, Prandtl number to the 1/3 power, Reynolds number to the 1/2 power, the Nusselt number for the laminar flat plate case. Turbulent case, bigger than 500,000 Reynolds numbers. My velocity profile, y over delta to the 1/7 power. Boundary layer thickness, delta over x, is 0.381 Reynolds number to the negative 1/5 power, minus 10,256 times Reynolds number to the negative 1 power. Again, experimentally determined values. Then the Nusselt number, Prandtl number to the 1/3, 0.037 Reynolds number to the 0.8 power minus 871, the Nusselt number in this case. Other geometries for external forced convection, mainly cylinders and spheres. For cylinders, pretty sure this is horizontal cylinders. Nusselt number is generally given by some constant, Reynolds number to some power, Prandtl number to the 1/3 power. So this happens a lot in these experimental cases where the equations were derived empirically. I have a lot of equations of this form, and just find the values of C and N based on the conditions. So for my cylinders, it's going to depend on the Reynolds number, and there's a table 7.7-2, page 328, which says what values of C and N to use based on the Reynolds number. Spheres is a more complicated equation, 2 plus 0.4 Reynolds number to the 1/2 power, plus 0.06 Reynolds number to the 2/3 power, Prandtl number to the 0.4, and then viscosities, mu infinity over mu wall. So those are the viscosities of the fluid at these different temperatures, so at T infinity and at T wall, 2 different viscosities, that ratio to the 1/4 power. And again, a good summary of all the equations to use for the various geometries for external forced convection in table 7.7 on page 354 to 355 should have at least the majority of the ones that you can use for each individual case. So again, a good thing to bookmark for the exam. Next up is inside tube, so internal forced convection. Here we have, again, it could be laminar, it could be turbulent. Transition in this case happens at a Reynolds number of 2300, laminar case less than 2300. If we have a constant heat flux, my Nusselt number is simply 4.36. If we have a constant temperature boundary, Nusselt number is simply 3.66. These assume that I have a fully developed case in the majority of my pipe. If that's not the case, if I'm looking at the entrance region before it's fully developed, I have a bit more complicated equation for that scenario. In the turbulent case, again, different equation for Nusselt number, 0.023 Reynolds number to the 0.8 power, Prandtl number to the n power, depending on whether the fluid is being heated up or cooled down. If the fluid is being heated up, I have 0.4, if it's being cooled down, it's 0.3. Again, this is assuming it's fully developed, so outside the entrance region. So those are the important equations for forced convection, the ones we see a lot. Of course, there's others in the textbook for other scenarios. Pre-convection, again, first case is the vertical plate, kind of like the horizontal plate case in forced convection, but upwards, that's the way buoyancy currents work for free convection. So it's a theoretical relationship on 418, but this empirical relationship is applicable in more scenarios, more values for Rayleigh numbers and things of that nature. So that's kind of more comprehensive. So that's one I wrote down here. But again, if you want to use the one on 418, that's fine too. So RA is GR times PR, the Rayleigh number. GR is a Grashof number given by G times beta, temperature difference, some length, x cubed over kinematic viscosity squared. And again, for this free convection case, it's this Rayleigh number which tells us whether it's laminar or turbulent. So that's going to be the value that we look to see what different values can be. So other geometries have, again, this kind of similar empirical relationship where the Nusselt number is some constant times Rayleigh number, GRPR, to the power m. And again, whatever scenario I'm dealing with, whatever geometry I have, whatever the value of the Rayleigh number is, there's different values for C and M. Just use the right one for the right case. That'll give you the Newsalt number. There's a few others as well. Again, your summary in table 9.3 on page 433 to 434. So such as this guy for horizontal cylinders, have the Newsalt number equation for that guy. So next up is some examples. Again, these basically the questions I had last year on the test. So again, last year was just those 3 questions. This year is going to be slightly different because again, we're going to have to kind of break things down into the different steps you have to make. So each question this year is going to be 1 step of these. So first example of carbon dioxide at 90 degrees Celsius atmospheric pressure flowing over a square horizontal plate at 60 meters per second. Side lengths of the plate are 60 centimeters. Plates maintained at a constant temperature of 10 degrees. Want to know the total heat transfer. And then secondly, what's the boundary layer thickness at the center of the plate? So first up, standard procedure. First thing is find my film temperature, average of the wall temperature, and T infinity. So wall temperature was 10, T infinity was 90. Yes, that's right. So film temperature there, 50 degrees Celsius or 323 Kelvin. So all the tables in the back of the book are in Kelvin. I believe this was air flown, no, carbon dioxide. Carbon dioxide flowing across here. So table A6, find carbon dioxide at this temperature 323. It may be between 2 temperatures, in which case you need to interpolate. So you might only have a temperature at 300 and at 350. 323 is roughly halfway between. So kinematic viscosity 975 10 to the negative 6 meters squared per second. Thermal conductivity 0.0185 watts per meter degree Celsius. Prandtl number of 0.763. Then from that I can find my Reynolds number. Velocity of 60. Distance or length 0.6 meters from my plate. Kinematic viscosity 9.75 gives me a Reynolds number of 3.69 times 10 to the 6th. That's bigger than 500,000, so this flow is going to be turbulent. So Newsalt number equation for the turbulent case, Prandtl number to the 1/3, 0.037 Reynolds number to the 0.8 power minus 871. So sticking those values for my Prandtl number, for the Reynolds number, gives me a Newsalt number of 5,270. Then fifth step, find H, K over length times Newsalt number. So K value, Newsalt number, length of 0.6 meters, gives me 162 watts per meter squared Celsius for my convective heat transfer coefficient. And again, standard convection equation, Q is H times A, T wall minus T infinity. So H of 162, area 0.6 squared, temperature difference of 90 minus 10, gives me 4,670 watts. Again, negative sign being optional, it just tells you the plate's being heated up or cooled down. So don't really care about the minus sign. Part B wants to know the boundary layer thickness at the middle of the plate. So very important distinction here at the middle of the plate. I want the boundary layer thickness depends on my value of X. Also depends on the Reynolds number, but that Reynolds number also depends on that value of X. So if I'm at the middle of the plate, my length is basically half of what it was before, meaning my Reynolds number is half of what it was before. So I don't want to use the same Reynolds number as in the first case, because that's at the end of the plate. I want to use the Reynolds number at the middle of the plate, half of it, 1.85 times 10 to the 6th. And then again, I know this is turbulent flow, so appropriate equation for turbulent flow for the boundary layer thickness, delta over X, is 0.381. Reynolds number to the negative 1/5 power minus 10,256. Reynolds number to the negative 1 power. Again, my X value is 0.3 meters in the middle of the plate. Stick in the value for the Reynolds number, gives me 4.71 millimeters essentially for the boundary layer thickness at the center of the plate. So that's example 1. Example 2, I have a 0.13 millimeter diameter wire exposed to an airstream at minus 30 degrees Celsius and 54 kilopascals. Flow velocity is 230 meters per second. Wire is electrically heated and is 12.5 millimeters long. I want to calculate the electric power necessary to maintain the wire's surface temperature at 175 degrees Celsius. And this is all horizontal. So again, standard procedure, find the film temperature, average of the two temperatures. So I have 175 for my wire, minus 30 for the air, so 72.5 gives me 246 Kelvin. Table A5 for air, find the viscosity, thermal conductivity, and Prandtl number at that temperature. Then again, this guy's at a weird pressure, so all these values, be careful. Some of them depend on pressure, some of them don't. So I'm not using kinematic viscosity because kinematic viscosity depends on pressure. Using normal viscosity. You can find the density. Again, there's a density in this table, but I don't want to use it because it's the wrong density. I want to find the density using the ideal gas law. So 54 kilopascals, R value for air 287, temperature 346 is 0.544 kilograms per cubic meter. Then my Reynolds number, density, velocity, diameter over viscosity. So density just found, velocity of 230, diameter 0.13 millimeters, and then the viscosity found from the table gives a Reynolds number of 786-ish. And then table 7-2 have this flow across a horizontal cylinder. So for flows across a horizontal cylinder, have this empirical relationship, the Nusselt number, some constant C times Reynolds number to some power, Prandtl number to 1/3. Based on this Reynolds number of 786, appropriate values for C and N, again, from that table, C is 0.683, N is 0.466. So just stick all those values in. So 0.683 for C, Reynolds number is 785.5 for Reynolds number, N value 0.466, and Prandtl number in there to the 1/3 power. Overall Nusselt number is 13.53. Then again, find H, K over D, times that Nusselt number. So K was 0.03. I'm not sure if I mentioned that previously from the table, but again, found from the table. And diameter 0.13 millimeters gives an H value of 3122 watts per meter squared degree Celsius. And then again, Q, HA, temperature difference. So area in this case, pi dl for my wire. So H is 3122, pi, diameter 13 millimeters. Length was 12.5 millimeters. And this temperature difference of 175 and -30 is a grand total of 3.27 watts for this guy. And then last question, I have a large vertical plate, 4 meters high, maintained at 60 degrees Celsius, exposed to atmospheric air, 10 degrees. I want to calculate the heat transfer if the plate's 10 meters wide. So in this case, I don't have any free stream velocity. So this is going to be a free convection case. There's nothing blowing across it. It's just the fact that the plate is heating up the air around it. So again, no velocity anywhere in the question. So assuming that's still air around it. So again, standard procedure as usual, film temperature. In this case is 35 degrees Celsius, 308 Kelvin. Properties of air at this temperature from the table. I am dealing with standard pressure here, so I can use kinematic viscosity from the table. The other thing I need for this case, because I'm dealing with free convection, is Grashof number has a beta in it, a volume coefficient of expansion. For any gas, that is just 1 over the temperature in Kelvin. So 1 over 308 gives me 0.00325 for the value of beta. And then Rayleigh number, GRPR, G beta, temperature difference, some length cubed, kinematic viscosity squared times Prandtl number. So all those values, G is 9.8, beta we just found. Change in temperature, 60 minus 10 is 50. The height of this plate was 4 meters, so 4 cubed. Kinematic viscosity 1.65, 10 to the -5 meters squared per second on the bottom, square that. Prandtl number 0.7 gives me a Rayleigh number of 2.62 times 10 to the 11th power. For the free convection case, there is laminar and turbulent situations. That is again defined by this Rayleigh number, GRPR. Anything less than 10 to the 9th is laminar, greater than 10 to the 9th is turbulent. So this is greater than that. So this falls in the turbulent regime. The equation we have for a Rayleigh number bigger than 10 to the ninth for a vertical flat plate is this empirical relationship. Nusselt number 0.8825 plus 0.387 Rayleigh number to the 1/6 power divided by 1 plus 0.492 divided by Prandtl number to the 9/16, whole thing to the 8/27 on the bottom. That entire thing squared. So plugging in all those numbers, get Rayleigh number 2.62 times 10 to the 11th, Grashof number and Prandtl number. Putting all that in gives me a Nusselt number of 716. Then again, standard last two steps, find H, K over D, or K over length in this case, times Nusselt number. So K was 0.0269. D, length of this plate is 4 meters. Nusselt number 716 gives an H value of 4.8 watts per meter squared degree Celsius. And then total heat transfer, H, 4.8. Area of my wall, 4 meters high, 10 meters wide, and temperature difference is 60 minus 10. Gives me a total heat transfer Q of 9,600 watts. So that's everything you're going to need to know for the test in a couple days. Again, just dealing with convection, going to have 15 kind of little questions as opposed to the 3 big questions we just saw. But again, you can expect to see a whole bunch of different geometries, flat plates, vertical, horizontal, cylinders, spheres, some forced convection, outside, inside, as well as free convection. So those are basically all the possible cases you're going to see. So hopefully you'll be ready for that, and hopefully it all goes well.